Okay, this video is on the topic of linear programming. Linear programming is a mathematical approach to solving logistics problems. So logistics problems, or logistics, is the process of planning, implementing, and controlling the effective and efficient flow of goods and services from the point of origin to the point of consumption. I would say logistics is, generally speaking, a problem of finding optimal solutions when given certain constraints. In logistics, we seek optimal solutions like maximum profit or minimum cost while satisfying certain restrictions, which we refer to as constraints, like amount of materials available, the amount of labor available, space available. These are restrictions that might be imposed that we refer to as constraints in the linear programming problem. So more specifically, some examples that can come up in linear programming are problems of finding maximum profit with certain budget constraints, or minimizing costs with constraints that involve the materials available or the labor available. You could do questions that involve scheduling times and rooms for classes for final exams. That would be a really complicated linear programming problem. Dealing with the scheduling of airlines and crews, warehousing, and delivery of products are logistics problems that can be solved with linear programming. There are companies whose whole business depends on logistics and solving logistics problems through very sophisticated linear programming models that are done on a computer, done really quickly, that take a lot of years of training and education to learn how to implement and to update and to maintain. There are companies whose whole entire business is logistics. So we'll start now with a very simplified example of a linear programming question that we can solve graphically. It's these examples that are solved graphically that are really the most simple ones, because generally if you're going to do a graph, you have only two variables to work with, and so you can manage it. And typically these questions that are set up to be solved actually by hand are sort of realistic, but not very realistic. So they are made up so that they could be done more easily by hand, and they give us a taste of what linear programming is about. But realistic linear programming questions could have thousands of variables and thousands of equations, and they have to be done on a computer to be more realistic, to make the questions more realistic, and it's only really solvable with a computer. We'll look at doing them graphically first, and then we'll move toward the simplex method, which is actually what you could use if you had more variables, even if you had thousands of variables and thousands of equations, and you put it in a computer, the computer would follow the simplex method. So let's go to this example. This question says a manufacturer of refrigerators must ship at least 100 refrigerators to its West Coast warehouses. Each warehouse holds a maximum of 100 refrigerators. Warehouse A holds 25 refrigerators already, and Warehouse B already has 20 on hand. It costs $12 to ship a refrigerator to Warehouse A and costs $10 to ship to Warehouse B. Union rules require that at least 300 workers are employed, and shipping to Warehouse A will require 4 workers for each refrigerator, while shipping to Warehouse B requires 2 workers for each refrigerator. How many refrigerators should be shipped to each warehouse to minimize the cost, and what is the minimum cost? Well, okay, first of all, union rules require at least 300 workers. That's kind of silly. Like, how would you need 300 workers when these warehouses only hold 100 refrigerators, it just seems ridiculous. But this is the point that I'm making about how these problems are sort of realistic, but they're made up to be something that we can manage doing these problems by hand in a way that works out neatly and simply and is meant to just sort of illustrate what linear programming is about, but it's not a very realistic example. So you can find all sorts of flaws with the problems that are typically done when you're expected to do it by hand. You say, this is not very realistic. Well, it's because it's trying to balance making it seem sort of realistic at the same time you can actually do it by hand with a reasonable amount of time. So, all right. When you're expected to do these by hand, you can expect that it's always going to be two variables that you're trying to solve for. And we can identify it usually by looking for the question mark. And here's a question mark. So it says, how many refrigerators should be shipped to each warehouse to minimize cost? So let's say X is the number. Say A is the number of fridges to ship to A. Let's make Y the number that we're going to ship to B. So we want to start off with identifying variables in any of these linear programming questions, whether you're going to do it with simplex method, use a calculator or computer, or whether you're going to do this completely by hand to graph it, you still have to identify the variables. Next thing to do would be to come up with the constraints. The constraints are always going to be linear, why it's called linear programming. And it's called linear programming because that term programming goes back to even really before there were actual computers that we programmed. So we just sort of looked at this as a method that you could go through a sort of program sequence of steps in the procedure, and that's where it's programming with linear constraints. So the constraints are the restrictions, and they're going to be, now of course not every restriction is always going to be linear, but even like more complicated nonlinear constraints, sometimes you just simplify to a linear constraint because they're just so much easier to work with. So all the ones where we graph, they're always linear. So what kind of constraints can we come up with? They create a region in our graph where we are sure that we'll have values that satisfy all the requirements. So let's start off with, this is a very typical constraint. It's not guaranteed always, but it's typical that you have non-negative values, right? You wouldn't have a negative number of fridges to be shipped to any warehouse, so you could begin with those as constraints. It says the manufacturer of the refrigerators must ship at least 100 refrigerators to its two West Coast warehouses, A and B. So I see another constraint there that says the total number to be shipped is going to be at least 100. It's greater than or equal to 100. It's either 100 or more. It also says that each warehouse holds a maximum of 100, so the total number at A has to be less than 100, the total number at B has to be less than 100, but hold on, we have this information that says A holds 25 already, B holds 20 already, so that further constrains the number. Let's say we could if X is the number going to A and it's got 25 already and it can hold 100 maximum, I can see that X is constrained to be less than or equal to 75, and I can see that the Y is going to be constrained to be less than 80 because B has 20 already, can only hold 100 maximum, so there's two additional constraints. It says it costs $12 to ship to A and $10 to ship one fridge to B. Those aren't constraints. Those are multipliers for the cost, and so I'll hold on to that when I look at my optimizing function. But there is this at least 300 workers that are employed, and further, shipping to A requires 4 workers. So every refrigerator that goes to A is going to take 4 workers, and each refrigerator traveling to warehouse B requires 2 workers. So we can capture that by saying if X was the number of refrigerators going to A, and each one requires 4, there's a multiplier there. 4 times X is the number of workers that would be required to ship X refrigerators to A. And because shipping to B requires 2 workers, you could say the number of refrigerators that go to B is going to be multiplied by 2 to get the number of workers, and it says requires at least, so this is the total number of workers, got to be greater than or equal to 300. Alright, and that finishes off my constraints. So we'll come back to use those to create the region of feasible solutions, but we also always need to get an objective function. Well, the objective function comes from whatever you're trying to optimize. In this case, the question was about minimizing cost, and what is the minimum cost? And we had some information that involves the cost here, $12 for each refrigerator that goes to A and 10 for each that goes to B. So you don't have any constraint there. You're trying to get the lowest cost with all of these constraints. So the objective function is the cost based on, it was $12 for each refrigerator that goes to A, and it's $10 cost for each refrigerator that goes to warehouse B. So this is my objective function. Represents the cost. We want to make that cost as low as possible. We could make it 0 if we didn't ship any refrigerators, but that wouldn't satisfy these constraints, right? If we had both X and Y 0, it wouldn't satisfy the constraint that we had to ship at least 100 refrigerators, or that we had to have 300 workers. So with all of these constraints, restrictions that are imposed, can we find a value that will minimize our total cost? So the graphical method would be to find a picture of the region that satisfies all these constraints. And because they're all lines, it's pretty easy to graph. So we'll go through one by one, looking at these constraints, drawing the lines, shading the regions that satisfy those constraints, and see if a region develops where all of those are met, and it's in that region that we'll look for the lowest cost. Knowing that X was the number of refrigerators that's shipped to warehouse A, I could form an axis, and knowing that I won't have a negative number that's shipped to A or a negative number that's shipped to B, I can draw a XY axis that's only the first quadrant and pick some sort of scale that seems reasonable to start here, and then you may, as you're doing a particular example, need to readjust what scale you're using and redraw. But with those constraints, if I take the first constraint that X plus Y is greater than or equal to 100, in order to graph the constraint, what you'll need to do is actually find the boundary of the constraint first. The boundary is when you just take the equality, just make it an equal. That forms the boundary of the constraint. Graph the boundary and then shade one side of the boundary. So this is a straight line. You can graph that by just getting 2 points. So we can do intercepts. If you make x equals 0, the y is 100. If we make y equals 0, then the x is 100. So that means I can plot 2 points that I know are on the boundary. And so with those 2 points forming the boundary, now I can graph the line. So that's the line that goes through those 2 points. But the constraint that I'm really trying to graph was this inequality, and it says we need to make sure that this quantity is greater than or equal to 100. So you could test any point on either side of that boundary and see if it's true, because being that this is the boundary, one side will be true, the other side will be false. In this case, if you tested like 0, 0, 0 plus 0 greater than or equal to 100, That's clearly false. So as soon as I recognize that a particular point on one side of the boundary is true or false, then I'll know which side to shade. Since that point came out false, it's everything on this side of the boundary would be false, and that means that we would actually shade in this direction from the boundary. I'm not going to shade yet because I want to actually finally shade the region that satisfies all the constraints simultaneously. So now let's move on and look at some of the other constraints and put them all together in one graph. So I'll look back at what other constraints do I have to work with. We've got x less than or equal to 75 and y less than or equal to 80. So that was one of the constraints. So technically, this is not a difficult one to manage. But formally, the process we go through is first identify the actual boundary, which is the line x equals 75. That's a vertical line. Looks like this. This is a graph of all the points where x is 75. But the constraint that I really wanted to graph was x less than or equal to 75. So again, I could test a point, but it's pretty clear that the points that would make that true are going to be this direction. They're going to be to the left of that boundary line. We also had the constraint that there was a further constraint that y had to be less than or equal to 80. So I can include that line now. Actually, the line is when it's equal. So this is the boundary line. So graphing the boundary line first, y equal to 80 might be somewhere like that. And then again, I could test a point, like 0, 0, to see if it's true, and actually is true. So I know that I would shade down, but it's pretty clear just immediately what points would make that true is shading downward from that boundary line. I'm not going to shade yet, again, because I want to shade just the region where all of them are true. It's beginning to take shape. Right now it's this triangle, but we still have another constraint. Okay, looking back at the question one more time and looking at all the constraints, we've got this one, this is done. Get the one more constraint here, 4x plus 2y greater than or equal to 300. You only need to graph the constraints. You generally don't graph the objective function. You might see somebody graphing it for the purpose of explaining why the whole thing actually works. But when you're just trying to get to the answer, you'll never actually graph the objective function as part of the linear programming method. So you don't graph this one. Just one more here, 4x plus 2y greater than or equal to 300. Okay, now in actually graphing the constraint, what we do is start off with the boundary. The boundary is just the equation when it's equal. You get 2 points on that boundary line. Generally, finding the intercepts is a good place to start. So if I make x equals 0, the y is 150. If I make the y 0, the x is going to be 75. So plotting these 2 points, 0, 150, that point's up here, and 75, 0, that's this point there. So the line passing through those 2 points looks like that. So once you've got the boundary line, the next thing to do is to figure out which side of the boundary line do you actually shade, and as long as you test a point that is not actually on the boundary line, it's fine. So 0, 0 is certainly an easy one to choose. It is clearly not on the boundary line. If I put 0, 0 in, I get 0 plus 0 greater than or equal to 300, and that's clearly false. Since it's false, and here's the boundary line, I know it's the other side where it would be true. It means that ultimately I want to shade in this direction. So now that I've got all the constraints, I'm looking for what region satisfies all the constraints simultaneously. It's got to be to the left of this line, below the y equal 80. It's got to be sort of above and to the right for this first constraint we had, the x plus y greater than or equal to 100, and the one that we just did, it's got to be sort of up and to the right. So it's this region. that satisfies all the constraints. Well, the last thing that we do in all of these linear programming questions by the graphical method, what we would do is we'd have to identify each of the corner points of this shaded region. This shaded region we call the region of feasible solutions. So it's a region in which you have solutions to the constraints, but I don't have my final answer because I want to know among all those feasible solutions, which one will give me the lowest cost. And it is a general principle of linear programming that fortunately you don't have to test every single point in that entire region. It has to be at one of the corners of the region of feasible solutions. So we just come up with that finite list of corner points and test those in the objective function to determine our answer, which one will give us the minimum cost in this case. Notice that doesn't mean that means I don't have to find every single intersection point of every one of these lines. I only need to find the intersections of some of the lines. In particular, it's the ones where they are corners of the region of feasible solutions. So finding these corner points, let's remember what these boundary lines, what equations produce these boundary lines, and then it'll be a matter of finding points that that lie on both of the boundary lines. This was the constraint 4x plus 2y. It was because I had to have greater than or equal to 300, but the actual boundary line is just where it's equal 300. And this boundary line, this was where x plus y equals 100. So I'm back to just looking at the equations because I want to find points that satisfy multiple equations. In other words, I'm solving a system. Some of these are really easy to solve, like what point makes this true and this true. I can find that point the fastest. It's immediate. This point right there is 75 for the x, 80 for the y. How about this point? Well, I know the x value. It's 75. And I also know that it is on this line right here that has x plus y equal 100. So if the x is 75, the y is 25. So all I'm doing is I'm just plugging 75 in for x because this has to be true also if you're at this point. So looking at a corner point, find the lines that intersect there and solve that system, and that's an easy one also to solve by substitution. This one's a little more challenged because it's the intersection of these two lines. So 4x plus 2y equal 300. That's one boundary line right here. This one going down like this. And then this one, this is the line x plus y equal 100. So this is a system that I have to solve. I need to figure out what point makes both equations true, and that would be the point where those two lines cross. So that is a question in and of itself. A calculator could do it. We could do it by hand. Let's do it by hand. You can solve the system by substitution, solving for one variable, substituting the result into the other, or you can solve it by the addition-elimination method. I think I'll use that one. To do that, I'm going to copy the first equation, just recopy it. And then I'm going to multiply the second equation by a -4. We could say multiplying that second row by -4 gives me an equivalent system. But you know, the reason I did that was so that I could add the two equations together. Because upon adding those two together, these terms will cancel out. I'll get an equation with one variable. It actually becomes -2y equals, this is -100. So we know y has to be 50. Now that I know y is 50, I could go back to any equation in this system, and the simplest one would be this. And since we know that x plus y is 100, and we now know that the y has to be 50, well, it's a simple question to find the x value. The x value has to be 50. Okay, now we've got the solution to this system, solving just that system means finding a point that makes both of those equations true. And the point that makes both of those equations true is a point that is on both lines, which is this point 50-50. That's what that point is right there. Now, you can't use the graph to know exactly what this point is. As you can see, my graph is not very accurate at all. So just because it happens to be, we have to do it algebraically, really, because even, sometimes the points will come out as fractions, and you could never tell from the graph. I mean, the graph can give you some hint as to approximately what it would be, and if you're way off, the graph could suggest, hey, there's a mistake, but we really can't use the graph unless we were actually doing the graph on a computer. Perhaps then you could get a very accurate point where they cross, but doing it by hand, you just use algebra to find the actual intersection. So now I've got this one, this one, this one. I only got one more. This point here, well, this one's pretty easy to solve for because we know the y is already 80 and it's an intersection with this line. So I need to create the system that has this equation and this equation. That is, the two lines that are crossing right here are the line 4x plus 2y equal 300 and the line y equal 80. So that's the system, and if this equation has to be true, you can just substitute that into the first one because they have to be both true. So we have to have 4x plus 2 times 80 equal 300. So 4x plus 160 has to equal 300. So 4x has to be, let's see, that's 140. So solving for x is 35. So now we know this point, 35 comma 80. So we're almost done. We just take these, we have 5 points, we're going to plug them into the objective function and choose which of these produces the lowest cost. Okay, so at this point we'll take each of these corner points, this point 3580, this point here 7580, this point 7525, and this point 5050. Take each of those corner points, plug it into the objective function. Remember the objective function we identified back at the beginning, 12x plus 10y as the cost. That's the objective function. So you can make a table where you take each corner point, specifically they have to be corner points of the region of feasible solutions, only the corner points of that shaded region. Take each of those corner points, plug it in the objective function, you are guaranteed to find a optimal solution at one of the corner points. Either it's the max or the min, whatever you're looking for. In this case we're looking for a minimum. So we found these 4 points, actually it was 4 points. And we'll just evaluate the objective function at each of these points. This point will satisfy all the constraints, and so if we if we sent 35 refrigerators to warehouse A and we sent 80 to warehouse B, and these were the costs involved, it's going to be a total cost of $1,220. Let's compare with another option. Sending 75 to warehouse A and send 80 to warehouse B. What's the total cost there? This is $1,700, so that's a higher cost. This will satisfy all the constraints. Total cost in this option, $1,150. That's $1,150. It's less than this option, so far this is our best option. We got one more to try. Sending 50 to each warehouse will satisfy all the requirements, all the constraints, all the restrictions that were imposed. What's the cost here? It's actually $1,100. So that turns out to be it. That's the optimal choice. Satisfies every constraint. In this case, it produces the minimum cost. So the answer is send 50 refrigerators to warehouse A and 50 refrigerators to warehouse B. This results in a minimum cost of $1,100 while satisfying all the imposed constraints. Okay, that's the end of this particular example. I hope it's been helpful.